Out there in the vast expanse of space, where the rules of physics twist into shapes we can barely comprehend, there exists a cosmic oddity so rare that spotting one feels like winning the universe's lottery. Picture not just one, not two, but 13 stars locked in an intricate gravitational dance, a Tredecuple star system, a place where night and day would be nothing but chaos, where the sky would burn with the light of a dozen suns. These celestial marvels defy everything we thought we knew about how stars behave and what astronomers have discovered lurking within them. Well, it's stranger than anything science fiction could dream up. Imagine standing on a planet, if one could even survive the gravitational tug-of-war, where the horizon is a swirling canvas of sunrises and sunsets in every direction, where shadows stretch and warp under the glare of multiple stars. But the real magic isn't just in their breathtaking spectacle, it's in the secrets they hide. How do 13 stars avoid tearing each other apart? What kind of planetary systems could possibly form in such turbulence? And why do some of these systems emit signals that make no sense according to our current understanding of physics? The answers are as puzzling as they are thrilling, and they're rewriting the textbooks on stellar evolution. This is the story of Tredecuple star systems, cosmic rarities that challenge our very understanding of the universe. Over the next few minutes, we're diving into the strangest discoveries astronomers have made about these gravitational tangles. From rogue stars that shouldn't exist to mysterious energy surges that leave scientists scratching their heads. Buckle up, because what you're about to learn will make you see the night sky in a whole new light. The universe, it turns out, has a flair for the dramatic, and Tredecuple star systems are its most dazzling performance yet. Deep within the Orion constellation, where starlight weaves through clouds of cosmic dust, astronomers stumbled upon a gravitational puzzle that redefined the limits of what we thought possible. This Tredecuple system, catalogued as Orion Complex 13, isn't just a cluster of stars, it's a celestial ballet gone rogue. 13 massive stars whirl around one another in a pattern so erratic it sent shockwaves through the astrophysics community. The discovery began with a flicker. Telescopes picked up rhythmic shifts in light from this region, not the steady pulse of a binary system, but a jagged, uneven stutter. When researchers mapped the orbits, the data defied every known model. Stars weren't following neat elliptical paths. Instead, they slingshot unpredictably, their trajectories more like tangled yarn than the orderly dances seen in smaller systems. What makes this chaos so baffling? In most multi-star systems, gravity creates a hierarchy. Stars pair off or orbit a central mass, keeping things stable. But here, the sheer number of massive bodies throws equilibrium out the window. Simulations collapse within centuries when modeling this system. The gravitational interactions are so complex, even supercomputers struggle to predict where a single star will be in 100 years. Then there's the mystery of survival. With so many stars crammed so close, they should have torn each other apart long ago. Yet this system persists, suggesting hidden forces, perhaps dark matter or undiscovered physics, are acting as cosmic glue. One theory, the stars might be trading energy in ways we've never observed, a gravitational game of hot potato that keeps them from collapsing into catastrophe. The implications are staggering. If stellar systems can thrive in such pandemonium, our textbooks on star formation might be missing entire chapters. Orion Complex 13 isn't just an oddity, it's a dare from the universe, challenging us to rethink how celestial bodies coexist, and this is only the first of its secrets. But the strangeness doesn't stop there. In another Tredecuple system, astronomers witnessed something even more bizarre: stars that seemed to blink out of existence without warning. At first, researchers thought they'd stumbled upon a monster black hole, silently devouring suns one by one. The data showed sudden, dramatic dips in light from multiple stars, as if something invisible were swallowing them whole. But when they looked closer, the truth was far more peculiar. This system, designated Kappa 13, plays host to what scientists now call the phantom eclipse phenomenon. Unlike the predictable dimming of a single star passing behind another, here the eclipses are chaotic, almost theatrical. With 13 stars orbiting at extreme angles, their paths crisscross in ways that create fleeting, overlapping shadows. One moment, 3 stars might align perfectly, blotting out a fourth from our view. The next moment, that same star reappears as another drifts into the foreground, casting its own shadow. The result, a celestial strobe light where stars vanish and reappear at random intervals, defying all attempts at prediction. What makes this illusion so disorienting is the sheer scale of the dance. In a typical binary system, eclipses follow a strict timetable like clockwork. But in Kappa 13, the gravitational interplay between so many massive bodies creates orbital instability. Stars wobble, their paths shifting slightly with each pass, which means no 2 eclipses ever repeat exactly. Early models suggested these events should be rare. Instead, astronomers observed them happening constantly, as if the system itself were alive, toying with the light. The implications go beyond mere spectacle. For decades, scientists assumed sudden stellar disappearances signaled black holes or rogue planets. Now, phantom eclipses force us to reconsider how we interpret flickers in the night sky. If a star winks out, it might not be dying, it might just be caught in the crossfire of a 13-star gravitational showdown. Even more intriguing, some of these eclipses last longer than physics says they should, hinting at yet undiscovered forces bending space and time within the system. Kappa 13 doesn't just challenge our tools, it messes with our instincts. When stars vanish without explanation, it's a humbling reminder that the universe still holds mysteries no equation can yet unravel. And this system has more surprises in store because lurking in its chaotic heart is something even stranger, something that shouldn't exist at all. Astronomers first detected the signal by accident, an erratic burst of radio waves pulsing from a Tredecuple system nearly 4,000 light-years away. At first, it seemed like cosmic static until researchers noticed the pattern. The pulses weren't random. They arrived in precise, repeating sequences like a heartbeat with an otherworldly rhythm. Dubbed the radio screamers, this system didn't just hum with gravitational chaos, it shrieked into the void with a signal that defied natural explanation. The strangest part, the pulses didn't match any known astrophysical phenomenon. Magnetars, neutron stars with crushing magnetic fields, can emit rhythmic bursts, but these pulses were too clean, too structured. Some sequences repeated in mathematical ratios, echoing patterns we'd expect from artificial sources. For a brief, electrifying moment, scientists entertained the unthinkable. Could this be a technosignature? The sheer improbability of 13 stars aligning with an intelligence capable of engineering such a signal made the idea tantalizingly controversial. Alternative theories scrambled for footing. One suggested a never-before-seen interaction between the system's magnetars, their magnetic fields tangling like live wires to produce coordinated bursts. Another proposed a bizarre form of stellar resonance, where the gravitational pull of 13 stars vibrated a rogue neutron star like a tuning fork, converting orbital energy into radio screams. Yet none of these fully explained the signal's eerie precision. Then came the curveball. Further observations revealed the pulses weren't just orderly, they evolved. Over months, the pattern shifted as if recalibrating itself. Natural processes don't adapt, technologies do. The debate reignited, splitting astronomers into camps. Some argued for an exotic natural explanation just beyond our current physics. Others whispered about ancient megastructures, hypothetical alien constructs harvesting stellar energy. The truth, we still don't know. The radio screamers remain astronomy's most tantalizing, maybe, a cosmic riddle balancing on the knife's edge between discovery and myth. And while scientists chase answers, one thing is certain: the universe, it seems, has a flair for the dramatic, and it's not done surprising us yet. Somewhere in the whirlwind of a Tredecuple system's chaos, a star decided it had enough and left in spectacular fashion. Astronomers tracking a system known as HD 1347 watched in disbelief as one of its stars was catapulted into the void at nearly 1/10 the speed of light, a velocity so extreme it shouldn't be possible through ordinary gravitational interactions. This wasn't just a star drifting away, it was a full-blown cosmic escape artist, tearing free of its siblings with enough energy to cross galaxies. Theories erupted about what could have launched this stellar fugitive. One leading idea involves an unseen predator lurking in the system's heart, an intermediate mass black hole, heavier than those left by dead stars but lighter than the supermassive monsters found in galactic centers. Such a black hole could have acted like a gravitational slingshot, flinging the star outward after a close encounter. Simulations show that in a system with 13 stars, chaotic orbits would regularly send stars diving toward the black hole, only for some to be hurled away with unimaginable speed. But there's another, even wilder possibility. What if the star didn't just get thrown, it got kicked? In hypervelocity collisions, two stars can slam together with such force that their merged remnant rockets away, a celestial bullet fired by the explosion's recoil. In HD 1347's crowded core, such collisions might be inevitable. The ejected star shows chemical anomalies in its light, hints of heavy elements that suggest it might have cannibalized a neighbor before its great escape. The Runaway's trajectory holds more clues. Unlike most ejected stars which drift in predictable arcs, this one weaves slightly, as if something massive tugged at it post-launch. That wobble fuels speculation. Could there be a second black hole or a dark matter halo warping its path? Either way, this star's defiance of gravity isn't just a fluke. It's a challenge to our models of how multi-star systems evolve. If stars can be fired like cosmic bullets, what else might these Tredecuple systems be capable of? And the Runaway's legacy doesn't end there. Its violent departure would have sent shockwaves through the system, potentially destabilizing other orbits. Some astronomers theorize that HD 1347's remaining stars are now locked in a slow-motion chain reaction, destined to collide, merge, or eject more members over millennia. It's a reminder that in these dense stellar societies, one rogue act can rewrite the fate of an entire system, and the universe has no shortage of surprises up its sleeve. Hidden in the chaos of a Tredecuple system named Luminous 13, where stars jostle for dominance like dancers in a crowded ballroom, astronomers found something that glittered, not with light but with literal cosmic bling. At the system's heart orbits a dying star so rich in carbon, its core may have crystallized into a diamond the size of a planet. This isn't poetic exaggeration, it's the mind-bending reality of the diamond core paradox, where the crushing gravitational ballet of 13 stars turns stellar death into something dazzling. The story begins with stellar alchemy. When a star like our Sun dies, it sheds its outer layers, leaving behind a dense core called a white dwarf, a smoldering ember of carbon and oxygen. Under normal circumstances, these dwarfs cool over billions of years, their cores solidifying into crystalline structures. But in Luminous 13, the rules get rewritten. Here, the gravitational tug of war between 13 stars compresses time itself. The white dwarf's cooling process, which should take eons, gets sped up to centuries as gravitational tides from its stellar siblings pump energy into its core like a cosmic forge. The result, a diamond of unimaginable purity, forged in a pressure cooker no lab on Earth could replicate. What makes this paradox so puzzling is the sheer improbability of the conditions. For a carbon-rich white dwarf to crystallize this fast, it needs two things: extreme pressure and a way to shed heat rapidly. The Tredecuple system provides both. As the stars whirl around one another, their gravity creates tidal forces that squeeze the dwarf's core. while stellar winds from its massive neighbors strip away its outer layers, cooling it faster than nature ever intended. It's like taking a red-hot iron and quenching it in ice, only on a scale that defies imagination. But the real kicker, this diamond isn't forever. The same gravitational forces that created it will eventually tear it apart. Simulations show that within millennia, the erratic orbits of luminous 13 stars will destabilize, sending one or more giants spiraling toward the dwarf. The collision would unleash enough energy to vaporize the diamond in seconds, scattering its carbon atoms into space like cosmic confetti. It's a bittersweet twist, a jewel born from chaos destroyed by it. This discovery forces us to rethink how materials behave under extreme conditions. If a Tredecuple system can turn a dead star into a diamond factory, what else might these gravitational maelstroms be hiding? The universe, it seems, isn't just stranger than we imagine, it's stranger than we can imagine. And luminous 13 is proof that even in the cold vastness of space, there's room for a little cosmic glamour. In the swirling chaos of a Tredecuple star system known as Crimson Cluster 13, astronomers witnessed something straight out of cosmic horror, a vampiric star gorging itself on its siblings. At the system's chaotic core, one massive star, dubbed the Devourer, has grown unnaturally bloated, its gravity stripping material from the other 12 in a slow but relentless feast. This isn't just stellar evolution, it's a celestial feeding frenzy where swirling rivers of plasma stretch between stars like grotesque umbilical cords, funneling stolen fuel into the Devourer's ravenous core. The mechanics of this cosmic heist are both mesmerizing and terrifying. As the Devourer and its victims orbit one another in tight, unstable loops, tidal forces peel away their outer layers, creating vast accretion disks of superheated gas. These glowing halos spiral inward at dizzying speeds, their friction generating X-ray flares bright enough to outshine entire galaxies. But the real shock came when spectrographs revealed the Devourer's secret. It's not just consuming, it's transforming. The stolen material has triggered exotic nuclear reactions in its core, fusing elements heavier than iron at rates that defy stellar models. This gluttony has dire consequences. Normally, stars this massive would explode as supernova within millions of years. But by constantly topping up its fuel supply, the Devourer has postponed its own destruction, growing so unstable that when it finally collapses, astronomers predict an explosion unlike anything ever recorded, a hypernova with energy surpassing 100 ordinary supernovae. The blast could sterilize nearby star systems and seed the galaxy with rare metals normally only forged in neutron star collisions. Even stranger, the Devourer's victims are fighting back. Some stars in the cluster show bizarre, lopsided shapes, evidence of violent gravitational tugs of war where they've managed to claw back some of their stolen plasma. Others eject jets of material perpendicular to the accretion disks, like cosmic fire hoses trying to blast the Devourer away. It's a dynamic battlefield where gravity, radiation, and magnetic fields wage an endless war, one that could rewrite our understanding of how stars live, die, and occasionally turn into monsters. For astrophysicists, Crimson Cluster 13 is more than a curiosity, it's a time bomb. By studying its chaotic ballet, they've realized similar vampiric systems might be lurking undetected across the galaxy. Their delayed explosions potentially responsible for mysterious gamma-ray bursts that appear without warning. If so, these celestial predators could be hiding in plain sight, masquerading as ordinary stars while secretly preparing to tear the sky apart. And that changes everything we thought we knew about the life cycles of the universe's most violent events. At the heart of an unnamed Tredecuple system 20,000 light-years from Earth, time itself bends to the will of 13 stars. Astronomers first noticed the anomaly when their instruments detected a discrepancy in the pulsing rhythm of a neutron star within the cluster. The pulses, which should have arrived like clockwork every 1.3 seconds, instead dragged, stretched out as if moving through cosmic molasses. This wasn't a mechanical error or interference. It was Einstein's theory of relativity playing out in its most extreme form, where gravity so intense warps the fabric of spacetime that time slows to a crawl. The culprit, a gravitational monster lurking at the system's core. While most Tredecuple systems balance their stars in chaotic but stable orbits, this one has a secret hierarchy. 12 stars whirl around a central pair, two neutron stars so close they nearly touch, their combined mass creating a gravity well deeper than any single star could produce. The effect is like a whirlpool in space-time, where every passing second for the neutron star near this pair ticks slower than a second for observers on Earth. If you could stand on one of those distant stars, your watch would crawl while clocks back home raced ahead. A year there might pass in what we'd experience as mere weeks. This phenomenon, called gravitational time dilation, isn't just theoretical. We observe milder versions near Earth's own gravity, while satellites in orbit must correct their clocks to account for tiny time shifts. But in this Tredecuple system, the effect is magnified to staggering extremes. Light from the innermost stars takes longer to escape the gravitational prison, stretching wavelengths into the red end of the spectrum. It's as if the stars are screaming in slow motion, their signals distorted by the crushing weight of spacetime itself. The implications ripple far beyond this one system. If time can be stretched this dramatically by 13 stars, imagine the distortions near supermassive black holes or in the early universe's densest regions. It raises eerie questions. Could entire civilizations rise and fall in what we'd perceive as a cosmic blink? And how many other Tredecuple systems hide similar anomalies, their secrets locked behind walls of bent time? For now, this system remains a laboratory for the universe's most brutal physics. Every pulse from its neutron star is a message from deep inside a gravitational funhouse, reminding us that even time, the one constant we thought we could rely on, is anything but absolute when 13 stars command the clock. Among the swirling chaos of stars in a Tredecuple system catalogued as Mirage 13, astronomers found a ghost, a presence so elusive it defied direct observation. This system should have 13 stars, yet telescopes only ever captured 12. The missing member wasn't hiding, it was invisible, detectable only by the way its gravity warped the light of its siblings, bending their glow into faint, shimmering arcs. This wasn't just a dark star, it was a cosmic phantom, and its identity became one of the most heated debates in modern astrophysics. The first clues came from anomalies in the system's motion. The 12 visible stars orbited an empty point in space as if tugged by an unseen force. When researchers mapped their paths, the math demanded a 13th object with the mass of at least 3 suns. Yet no light, no heat, no radio emissions emerged from the spot. Gravitational lensing, the bending of starlight around massive objects, revealed its presence, stretching the images of background stars into eerie, smeared halos. Whatever lurked there wasn't just dark, it was a master of disguise, cloaking itself from every wavelength we could throw at it. Theories exploded. Could it be a rogue neutron star, the collapsed core of a dead giant, so cold and dense it emitted no radiation? Or something more exotic, a primordial black hole, forged in the chaos of the early universe, small enough to evade detection yet massive enough to bend spacetime like a cosmic boulder in a stream? The third possibility rattled even seasoned scientists. What if it was neither? Some models suggested an object beyond our current classification, a dark relic, a hypothetical remnant of exotic matter left over from the Big Bang, invisible to all but gravity itself. The implications are staggering. If this phantom is a primordial black hole, it could reshape our understanding of dark matter, offering a glimpse into the universe's first moments. If it's a neutron star, its silence challenges everything we know about stellar corpses. And if it's something entirely new, well, that's the spine-tingling beauty of Mirage 13. It dances on the edge of discovery, taunting us with a question we can't yet answer. In a cosmos full of light, what else lingers in the shadows, waiting to rewrite the rules? In the heart of a Tredecuple system catalogued as Nova Quadrant 13, astronomers witnessed an event so perfectly timed, it bordered on orchestrated 13 stars erupting in unison, their surfaces convulsing with solar flares so violent the combined light briefly outshone their host galaxy. This wasn't random stellar tantrum, it was a cosmic symphony of destruction, each flare igniting within minutes of the next, as if some unseen conductor had raised a baton and unleashed chaos. The odds of such perfect synchronization are astronomical. Solar flares typically erupt when a star's twisted magnetic field snaps, releasing energy in violent bursts, but these are isolated events, unpredictable as earthquakes. For 13 stars to detonate in lockstep suggests something far stranger. Magnetic fields entangled across light years, binding the stars like puppets on invisible strings. Spectrographic data revealed the truth. Loops of superheated plasma stretched between the stars, tracing pathways where magnetic field lines had knotted together over millennia. When one star's field destabilized, the shockwave raced along these cosmic filaments, triggering eruptions in the others like a chain of dynamite. The implications are terrifying. If this stellar domino effect can occur naturally, entire multi-star systems might be sitting on a fuse. Imagine a civilization orbiting one of these stars, its skies suddenly filled not with one angry sun but 13, each flare stripping atmospheres, frying electronics, and bathing planets in lethal radiation. The sheer scale of destruction would be unimaginable, and the scariest part, Nova Quadrant 13's flares weren't even the worst-case scenario. Simulations show that in tighter systems, such an event could escalate, with each flare destabilizing neighboring stars further, leading to a runaway reaction capable of ripping the entire system apart. Yet amidst the chaos, there's eerie beauty. The flares didn't just erupt, they echoed. Light from each explosion bounced off the others, creating interference patterns that painted the system's gas clouds with shimmering, ripple-like halos. For a brief moment, the stars weren't just destroying, they were communicating, their violent language written in wavelengths no telescope had ever captured before. The mystery deepens when you ask why this happens at all. One radical theory suggests these flares aren't accidents, but resets a way for overcrowded star systems to shed excess energy before it tears them apart. Another posits that entangled magnetic fields are cosmic relics, leftovers from the system's birth when all 13 stars shared a single, ancient nursery of gas and dust. Whatever the truth, Nova Quadrant 13 proves that even in the cold void of space, stars don't always act alone. Sometimes they scream together. Buried in the depths of intergalactic space, drifting like a ghost from a time before galaxies took shape, there exists a Tredecuple system so ancient its stars remember the universe's infancy. Designated Erebus 13, this relic is older than the Milky Way itself, a cosmic fossil with a composition so pristine. Its stars contain barely a whisper of heavy elements. Unlike younger systems forged from recycled stellar debris, Erebus 13's members are made of almost pure hydrogen and helium, the raw materials of the Big Bang. It's as if this system was frozen in time, escaping the chemical pollution of supernova and galactic collisions for nearly 13 billion years. How did such a fragile arrangement survive so long? The answer lies in its exile. Erebus 13 drifts in the void between galaxies, far from the gravitational tug of war that shreds star clusters in denser regions. But isolation alone doesn't explain its persistence. The system's stars are bound in an unusually wide, lazy orbit, their movements more like a drifting cloud than the frantic dances seen in younger Tredecuple systems. This gentle rhythm reduces the chance of catastrophic collisions, granting the stars an improbable longevity. Astronomers compare it to a group of dancers spaced so far apart they never touch, swaying to a slow-motion tune untouched by time. Yet the real treasure here isn't just the system's age, it's what its stars reveal about the early universe. Their metal-poor composition suggests they formed from gas untouched by earlier generations of stars, offering a snapshot of cosmic conditions before heavy elements existed. Studying their light is like reading a diary from the universe's first chapters, written in spectral lines unmarred by later contamination. One star in particular, Erebus Prime, shows lithium levels that defy models of stellar evolution, hinting at physics we've yet to understand. But Erebus 13's greatest riddle is how it avoided annihilation. Over billions of years, galaxies grow by cannibalizing smaller systems, yet this one slipped through the cracks. Some theorists propose it was ejected during an ancient galactic collision, flung into the void like a stone from a slingshot. Others suggest it's a rare survivor from a population of primordial star systems, most of which were torn apart and digested by larger galaxies. If true, Erebus 13 isn't just an oddity, it's a messenger from a lost era, carrying secrets about how the first structures in the cosmos formed and fell. Now, as telescopes probe deeper into its ancient light, astronomers face a haunting possibility. This system might be the last of its kind. If others like it existed, they're long gone, consumed by the relentless growth of galaxies. That makes Erebus 13 more than a scientific curiosity. It's a cosmic miracle, a flickering candle held against the dark, showing us a universe we can scarcely imagine. And in its fragile dance of 13 stars, we might finally find answers to questions we didn't even know to ask. Among the swirling chaos of a Tredecuple star system, where gravity tugs from every direction, there's a cosmic crime scene unfolding. Protoplanetary disks, the birthplaces of planets, twisted and torn into shapes no artist could conceive. In most star systems, these disks are serene, flat rings of gas and dust where worlds slowly coalesce. But cram 13 stars into the mix and the serene becomes surreal. The disks don't just warp, they fracture into spirals, loops, and even hourglass shapes, as if some unseen hand grabbed them and gave them a violent twist. Take the system catalogued as Carousel 13. Here, infrared telescopes revealed a protoplanetary disk stretched into a helix, its material spiraling outward like a cosmic slinky. The culprit, gravitational tides from multiple stars yanking the disk in opposing directions, pulling it apart faster than planets can form. In another system, the disk isn't just warped, it's shredded into debris arcs resembling the spokes of a broken wheel. These aren't just aesthetic oddities, they're death sentences for budding planets. Normally, dust grains in these disks gently collide, sticking together to form pebbles, then boulders, then planets. But in a Tredecuple system, the constant gravitational turmoil kicks debris with such violence that collisions don't build, they obliterate. The implications for habitability are grim. Even if a planet somehow manages to form, its fate is bleak. Orbital stability in these systems is a myth. A world might be flung into the frigid outer darkness one moment and hurled into a stellar inferno the next. Radiation from 13 stars would bombard any surviving planets, stripping atmospheres and baking surfaces sterile. And the sheer temperature swings from the glare of multiple suns to the shadows of their eclipses would create weather patterns of unimaginable ferocity. Yet the most fascinating twist isn't the destruction, it's the exceptions. In a handful of these systems, astronomers have spotted survivor disks, small pockets of gas and dust sheltered in gravitational eddies like calm eyes in a hurricane. These regions might just be stable enough to birth planets, though not as we know them. Any worlds forming here would be alien beyond reckoning, tidally locked to multiple stars. Their skies a permanent kaleidoscope of sunrises and sunsets, their geology shaped by gravitational kneading. The discovery of these warped disks doesn't just rewrite the rules of planet formation, it erases them. If a system with 13 stars can somehow, against all odds, harbor planets, then our definition of habitable might need to stretch as far as those twisted disks themselves. The universe, it seems, loves a challenge, and in the chaos of Tredecuple systems, it's playing by its own rules. In the tangled web of a Tredecuple system called Mirage Heart, astronomers witnessed light bending the rules of time itself. A supernova's flash that shouldn't have been visible until 2,000 years from now. Yet there it was, repeating like a cosmic echo, the same burst of energy flickering across telescopes a second time decades after the initial explosion. This wasn't a glitch or an instrument error. It was the universe performing sleight of hand, where light became trapped in a labyrinth of warped spacetime and quantum trickery, forcing scientists to confront a question: can light be stolen from the future? The first clue came from the system's peculiar geometry. Mirage Heart cradles a neutron star so dense, its gravity twists space into a knot. When the supernova's light raced outward, some photons took a shortcut through this distorted region, arriving years ahead of their expected schedule, like a train cutting through a mountain tunnel while others take the long route around. But the real shock came when researchers noticed fainter echoes of the same explosion appearing at irregular intervals, some delayed by decades. These weren't just gravitational mirages. They behaved like light caught in a cosmic eddy, swirling back into view as if the universe had pressed rewind. One radical explanation points to quantum loops in the system's circumstellar nebula, a soup of ionized gas so turbulent it might have trapped photons in an endless game of pinball. Normally, light travels in straight lines, but here, magnetic fields could twist its path into closed circuits, releasing it in staggered bursts as the loops destabilized. Imagine throwing a ball into a hall of mirrors and watching it ricochet back at you minutes or years later. That's the nightmare astronomers faced when trying to map Mirage Heart's timeline. Then there's the space-time warping theory. With 13 stars crammed so close, their combined gravity might have knitted space into a fractal. A shape so folded and creased, light could take multiple paths to the same destination, like a maze with infinite exits. If true, we're not just seeing echoes, we're glimpsing alternate routes through the fabric of reality, where a single event splinters into a hall of mirrors stretched across time. The implications are staggering. If light can be delayed, deflected, or even stored this way, ancient supernova might still be flickering in hidden corners of the cosmos, their messages from the past arriving out of order. Worse, what if we've misstated entire cosmic events because their light took a detour we couldn't see? Mirage Heart isn't just bending light, it's bending the very foundations of how we measure the universe's history. And that means some chapters of our cosmic story might need rewriting. In the swirling chaos of a Tredecuple system known as Prism 13, something impossible happens daily. Stars change color right before astronomers' eyes. Not the gradual shifts of aging suns, but violent, rapid transitions from crimson to violet, gold to emerald, as if the cosmos itself were tuning a celestial television set. At first, scientists blamed faulty instruments. Then they saw the data, entire stellar spectra rewriting themselves in real time, their chemical signatures blurred beyond recognition. This wasn't stellar evolution, it was interstellar sleight of hand, where the universe's most basic rule, that a star's color reveals its temperature and composition, got tossed out the window. The culprit, a phenomenon called plasma lensing. Between the stars of Prism 13 drift vast, invisible clouds of superheated gas, remnants of ancient supernova or stellar collisions. These clouds aren't uniform, they're riddled with density variations, like swirls in a cosmic latte. When starlight passes through them, the plasma bends different wavelengths by different amounts, acting like a prism on an astronomical scale. Red light might get deflected around a dense knot, while blue light punches straight through, scrambling the star's apparent color from our vantage point. The effect's so extreme that a single star can appear to split into multiple spectral doppelgangers, each showing a different, fake temperature. What makes Prism 13 unique is the scale of the illusion. Most interstellar gas distorts light subtly, if at all. Here, gravitational interactions between 13 stars churn the plasma into ever-shifting lenses, creating what astronomers call cosmic weather, localized temporary conditions that alter how we perceive the system. One week, a blue giant might masquerade as a cool red dwarf. The next, a neutron star could seem to emit the spectrum of a youthful Class O star. It's a hall of mirrors where every observation comes with a disclaimer: proceed with caution, reality may differ. The implications stretch beyond mere spectacle. For decades, astronomers have relied on spectral analysis as their gold standard for studying stars. Prism 13 exposes the fragility of that trust. If a star's light can be so easily doctored by interstellar plasma, how many other systems have we misclassified? Could some red giants in crowded clusters actually be hotter stars in disguise? The answer might rewrite catalogs across the galaxy, yet the chaos holds an unexpected gift. By studying how the lenses warp light, researchers can map the invisible plasma itself, a technique akin to tracing ripples in a pond to find submerged obstacles. Already, these distorted starlights have revealed filaments of ionized gas strung between the stars like spider silk, structures too faint to detect otherwise. In a twist of irony, the system's greatest deception has become its most transparent truth, offering a new way to see the unseen. Prism 13 doesn't just challenge our tools, it confronts our arrogance. In a universe where light itself can lie, perhaps the only certainty is that the cosmos will always find new ways to surprise us. And somewhere in that chromatic mirage between the real and the reflected, the universe is whispering a lesson. Sometimes to find the truth, you must first learn how easily it can hide. Deep within the tangled orbits of Tredecuple system Halo 13, astronomers found a cosmic contradiction. A star that glows with visible light yet emits no detectable heat. This isn't a trick of the lens or a data error. Spectrographs confirm its surface registers near absolute zero, colder than the void of space itself. How can something shine so brightly while radiating less warmth than a snowflake? The answer might rewrite our entire stellar classification system. The leading theory points to a failed brown dwarf, a star too small to ignite hydrogen fusion, left to cool over eons. But there's a problem. Brown dwarfs fade as they chill, eventually becoming invisible infrared emitters. This object defies that fate, glowing with steady blue-white light despite its icy temperature. Some researchers propose it's a quark star, a hypothetical object where matter collapses into exotic particles under gravitational pressure, emitting light through processes we barely understand. Others suggest something even stranger, a dark star, powered not by fusion but by annihilating dark matter particles in its core, creating visible photons without the accompanying heat. Then there's the location factor. Nestled among 12 fiercely active siblings, this cold star shouldn't exist. The radiation and stellar winds from neighboring giants should have stripped its atmosphere or heated it beyond recognition. Instead, it sits untouched like a diamond in a furnace, its light unblemished by the chaos around it. Some astronomers speculate it's protected by an impossibly strong magnetic field, bending radiation around it like an invisible shield. Others wonder if it's not a star at all, but a primordial relic, a fragment of the early universe's quark-gluon plasma, somehow surviving billions of years to glow defiantly in modern times. The implications ripple far beyond Halo 13. If this object represents a new stellar class, how many others have we missed, dismissed as instrument glitches? Could the cosmos be hiding entire populations of these cold luminaries, rewriting the rules of stellar life and death? For now, the paradoxical star keeps its secrets, shining a light quite literally on how much we still have left to discover. There's a corner of the cosmos where chaos gives way to harmony, a Tredecuple system called Symphony 13, where stars don't just orbit, they sing. Here, the gravitational dance follows ratios so precise they mirror musical scales, with stars pulsing in Fibonacci sequences and perfect fifths. their movements locked in celestial rhythms that have endured for millennia. It's as if the universe itself composed a grand opus, each star a note in an interstellar sonata. The discovery began with a flicker in the data. Astronomers tracking this system noticed its stars weren't just moving, they were syncopating. One star's orbit took exactly 1.618 times longer than its neighbors, matching the golden ratio. Another pair echoed the Fibonacci sequence, their orbital periods adding up like numbers in the famous spiral. These weren't coincidences, they were resonant harmonies, gravitational pull and momentum balancing so exquisitely that the system became self-correcting, like a clock that winds itself. What makes these harmonies so rare is the sheer improbability of their stability. In most multi-star systems, even tiny gravitational nudges grow into chaotic tumbles over time. But in Symphony 13, the stars' precise ratios create feedback loops that dampen chaos. When one star drifts slightly out of step, the others tug it back into alignment, their collective gravity acting like a metronome for the cosmos. It's the astrophysical equivalent of a choir correcting a singer's off-key note, except this choir has been in tune for millions of years. The implications ripple beyond mere fascination. Resonant orbits like these could be the key to understanding how overcrowded star systems avoid self-destruction. In younger systems, these harmonies might guide planets into stable niches, creating pockets where life could endure despite the stellar frenzy. And for astronomers, they offer a cosmic tuning fork, a way to measure the subtle gravitational whispers between stars that would otherwise be lost in the noise. Yet the greatest mystery remains why Symphony 13 plays by these rules. Did the stars form this way, their orbits composed in the nursery of their birth cloud? Or was it a later arrangement, a chance encounter that somehow snapped into perfect order? The answer might lie in the system's unusual stillness. Unlike most Tredecuple systems, where stars jostle like bumper cars, Symphony 13's members keep a respectful distance, their orbits wide and graceful, as if they've all agreed to follow the same sheet music. For now, this celestial concerto continues, its rhythms a silent testament to the universe's hidden order. And somewhere in those precise mathematical dances, there's a lesson. Even in the chaos of the cosmos, harmony finds a way. Whether by accident or design, Symphony 13 proves that the universe has a soundtrack, and sometimes, if you listen closely, the stars themselves are the musicians. Most Tredecuple systems burn bright and fast, their stars destined to spiral into chaos or fling each other into the void. But one rebel system defies the odds. Designated Anchor 13, this cosmic oddball has maintained near-perfect stability for billions of years, its 13 stars tracing orderly loops as if guided by an invisible hand. The secret to its harmony, astronomers suspect a cosmic puppeteer lurking in the shadows, not a black hole or neutron star, but something far more elusive, a concentrated halo of dark matter, wrapping the system in a gravitational embrace no telescope can directly see. The clues are written in the star's movements. Ordinarily, systems this crowded should experience wild orbital fluctuations, their gravity playing a relentless game of tug-of-war. Yet Anchor 13 stars move with uncanny precision, their velocities subtly faster than visible mass alone can explain, as if something massive but invisible were tightening the reins. When researchers mapped the gravitational forces required to maintain this order, the math revealed a startling gap. The system behaves as though it contains 5 times more mass than its luminous stars account for. Dark matter, long thought to exist primarily in vast, diffuse clouds around galaxies, may here be clumped tightly enough to shape individual stellar orbits. This discovery flips the script on dark matter's role in stellar evolution. Most models treat it as a background player, its gravity gently sculpting galaxies over eons. But in Anchor 13, it appears to be an active architect, its concentrated mass acting like celestial glue. Some theorize the system formed inside a primordial knot of dark matter, a dense relic from the universe's first second that somehow avoided dispersal. Others suggest the stars themselves trapped dark matter over time, their collective gravity acting like a net to corral and compress the invisible particles into a stabilizing scaffold. The implications ripple beyond this one system. If dark matter halos can anchor Tredecuple systems, might they also explain other cosmic survivors like the mysterious stellar fossils that defy aging? And could this hidden infrastructure influence planet formation in unexpected ways? Anchor 13 doesn't just challenge what we know about dark matter. It suggests we've barely scratched the surface of how it shapes the universe's most dazzling structures. Yet the greatest puzzle remains how to prove it. Dark matter refuses to emit, absorb, or reflect light, leaving only gravitational fingerprints as evidence. Future telescopes may hunt for gamma-ray signatures from hypothetical dark matter collisions, or measure how the system lenses distant starlight in ways ordinary math can't explain. For now, Anchor 13 stands as both a revelation and a riddle, a cosmic waltz where the lead dancer remains forever in the shadows, its presence felt but never seen. And that changes everything we thought we knew about the hidden forces holding the universe together. In the depths of a distant Tredecuple system, an interstellar light show defies the cold darkness of space, a nebula glowing with unearthly blues and greens, wrapping 13 stars in a luminous shroud unlike anything else in the cosmos. Designated the Veil of Ithaca, this phenomenon isn't powered by starlight alone, but by something far stranger: trillions of organic molecules stirred to life by the relentless ultraviolet fury of its stellar host. The result, a space aurora spanning light years where the nebula pulses and flickers as if breathing, its eerie radiance visible even from neighboring star systems. The magic lies in chemistry pushed to extremes. Most nebulas glow from ionized gas, their colors dictated by elemental compositions: red for hydrogen, blue for oxygen. But the Veil of Ithaca's shimmer comes from complex carbon chains, the same building blocks of life, electrified by the system's overlapping UV radiation fields. When the ultraviolet onslaught strikes these molecules, they don't just heat up, they fluoresce, releasing energy as vivid photons in a process akin to bioluminescent algae on Earth, but scaled to cosmic proportions. The effect transforms the nebula into a celestial jellyfish, its tendrils rippling with light that shouldn't survive the vacuum of space. What makes this spectacle even more surreal is its instability. With 13 stars bombarding the nebula from all angles, the light patterns shift hourly. One region might flare emerald as a massive star's UV surge excites formaldehyde molecules. Another dims to indigo when passing dust clouds momentarily shield it. Telescopes have captured waves of color racing across the nebula at speeds impossible for physical material. Proof the glow isn't just reflecting light, but actively regenerating as molecules absorb and re-emit energy in a frantic dance. Yet the real mystery isn't the glow itself, but its longevity. Organic molecules in space typically disintegrate under such intense radiation, yet here they thrive. Astronomers suspect the system's unique geometry creates safe havens, shadows where molecules briefly shelter before being swept back into the fray, like cosmic fireflies repeatedly dodging a floodlight. Others theorize the molecules are replenished by comets, their icy bodies vaporizing as they plunge near the stars, seeding the nebula with fresh material. The implications are profound. If complex organics can endure this stellar gauntlet, it raises tantalizing questions about where and how life's ingredients might persist in hostile environments. The Veil of Ithaca isn't just a pretty anomaly, it's a laboratory for the universe's most resilient chemistry. And somewhere in that shimmering expanse, nature might be proving that life's building blocks are far tougher and far more universal than we ever dreamed. In the swirling heart of a Tredecuple system known as Gemini's knot, two stars defy the laws of classical physics, not just orbiting each other, but seemingly thinking as one. These stellar twins, catalogued as Epsilon 1 and Epsilon 2, exhibit behavior so bizarre it makes quantum physicists question everything. Their light pulses in perfect unison. Their magnetic fields flip polarity simultaneously across millions of miles, and their spectral lines shift in tandem as if controlled by invisible strings. This isn't mere synchronization. It's quantum entanglement, the same spooky action at a distance Einstein famously doubted playing out on a scale so massive it rewrites the rules of how the universe connects. The phenomenon first came to light when astronomers noticed an impossible correlation. Every time Epsilon 1 emitted a gamma-ray flare, Epsilon 2 mirrored it within picoseconds, far faster than light could travel between them. At first, researchers dismissed it as coincidence until the pattern repeated hundreds of times with statistical precision beyond random chance. Then came the real shock. When one star's spin rate slowed due to magnetic braking, its twin adjusted instantaneously, as if sharing an unseen cosmic tether. The stars weren't just communicating, they were entangled, their quantum states linked across the void in defiance of space and time. How does entanglement persist in an environment as chaotic as a Tredecuple system? On Earth, entangled particles decohere at the slightest disturbance. A passing photon or vibration shatters the bond. Yet here, two stellar behemoths, each a maelstrom of plasma and magnetic storms, maintain this delicate quantum dance amidst the gravitational fury of 11 other stars. One radical theory suggests their cores host exotic matter, quark-gluon plasmas or Bose-Einstein condensates acting as quantum anchors that resist decoherence. Another posits that the system's extreme gravity warps spacetime enough to create a protective bubble, shielding the entanglement like an invisible Faraday cage. The implications are staggering. If quantum correlations can scale to stars, does the universe remember hidden connections between seemingly isolated objects? Could entanglement weave through black holes or galactic filaments, creating a cosmic web of instant correlations we've never noticed? Some theorists even speculate that Gemini's knot might be a natural quantum computer. Its entangled stars performing calculations through their synchronized states, a process as unfathomable as it is beautiful. Yet the greatest mystery remains why. Entanglement typically requires particles to interact physically before separating. These stars, born light years apart in the system's infancy, should never have shared such intimacy. Unless, and here's the spine-tingling part, their entanglement isn't a rare accident, but a fundamental feature of how multi-star systems form. If true, the universe might be far more interconnected than our textbooks dare suggest. And somewhere in the flickering light of those two stars, physics itself whispers a question. What else have we missed? Tucked between the 13 stars of Carina's web, a cosmic trespasser was caught red-handed, a rogue gas giant barreling through the system like a bull in a china shop. This wasn't just any drifting planet. It was a Jupiter-sized behemoth ejected from some forgotten star system, and now carving a path of chaos through one of the universe's most fragile gravitational ballets. What unfolded next was a celestial chain reaction so violent, it rewrote the rules of how planets and stars interact. The first sign of trouble came when astronomers noticed a subtle wobble in one of the system's outermost stars, its orbit stretching into an elongated ellipse overnight. Then, like dominoes tipping, two more stars began veering off course, their usual paths distorted by the intruder's gravitational pull. Unlike the gentle nudges of a passing comet, this gas giant packed enough mass to yank entire stars from their orbits, sending shockwaves through the system's delicate equilibrium. The real danger lay in the domino effect. In a Tredecuple system, stars orbit in a precarious balance, remove one piece, and the rest collapse into chaos. As the rogue planet plowed deeper, its gravity stirred the pot, flinging stars into trajectories that crisscrossed like tangled spaghetti. two stars now on collision courses began spiraling toward each other in a slow-motion dance of doom. Another, caught in the planet's gravitational slingshot, was hurled outward at breakneck speed, destined to wander the interstellar void forever. What makes this scenario so terrifying is its inevitability. In crowded systems like Carina's Web, space is at a premium. Stars orbit within stone's throw distances, leaving no room for error. A passing rogue planet doesn't just nudge them, it turns their orderly dance into a mosh pit. Simulations show that in the worst-case scenario, such an intrusion could trigger a hypervelocity cascade, where stars ricochet off one another like billiard balls, some ejected entirely, others merging in cataclysmic explosions. Yet amidst the destruction, there's a silver lining. These chaotic encounters might be the universe's way of pruning unstable systems. Just as forest fires clear dead wood, rogue planets could weed out stars teetering on the edge of gravitational collapse, leaving behind leaner, more resilient survivors. And for astronomers, the aftermath offers a rare glimpse into the raw physics of star formation, how systems adapt or shatter under pressure. For now, the gas giant continues its lonely journey, leaving a trail of stellar upheaval in its wake. But its legacy lingers, proof that even in the vastness of space, no system is an island. One stray planet can rewrite the fate of 13 stars, a humbling reminder of how fragile cosmic order truly is. Deep in the whirlwind of a Tredecuple system known as the gamma-ray chorus, stars don't just burn, they scream. Every few weeks, this cosmic ensemble erupts in a synchronized blast of gamma rays so powerful, astronomers mistook the first detections for colliding black holes. But the truth is stranger still. These aren't random outbursts, they're coordinated, almost like stellar musicians striking the same chord across millions of miles. And the conductor, possibly a hidden pulsar, spinning at the system's heart, a cosmic metronome orchestrating chaos into perfect, deadly harmony. The patterns are eerily precise. Gamma-ray telescopes have clocked bursts from up to 6 stars flaring within milliseconds of each other, their high-energy emissions overlapping in a lethal crescendo. Normally, gamma-ray bursts signal catastrophic stellar deaths or neutron star collisions, rare, isolated events. Here, they're routine, as predictable as a heartbeat and just as puzzling. The key lies in the system's tangled magnetic web. Spectrographs reveal filaments of magnetized plasma arcing between the stars, intertwining their magnetic fields like threads in a loom. When one star's field snaps under strain, the shockwave races along these filaments, triggering sympathetic eruptions in the others, a domino effect of destruction. But the real enigma is the central engine. Buried in the gamma-ray chorus's core lurks an object so dense it warps the orbits of nearby stars. Some researchers argue it's a pulsar, a rapidly spinning neutron star with a magnetic field trillions of times stronger than Earth. As it rotates, it could act like a dynamo, pumping energy into the surrounding plasma and forcing the star's magnetic fields into lockstep. Others propose something darker, a quark star, an ultra-dense remnant where matter collapses beyond neutrons into exotic particles, capable of emitting gamma rays in pulses so regular they mimic a cosmic clock. The implications rewrite stellar physics. If a single object can synchronize gamma-ray bursts across multiple stars, it suggests a previously unknown form of energy transfer, one where magnetic fields act like cosmic telegraph wires, carrying devastation at near light speed. Even more unsettling, the bursts are growing stronger. Recent observations show the gamma-ray chorus's output increasing by roughly 5% per year, as if the system is building toward an unfathomable finale. Whether that climax will be a hypernova, a magnetar's birth, or something entirely new, no one can say. But one thing's certain, when this cosmic choir reaches its crescendo, the universe will hear it. Amid the cosmic frenzy of a Tredecuple system named Sol's Echo, astronomers spotted something that shouldn't exist, a star so eerily similar to our own sun. Its spectral fingerprint matches nearly atom for atom. The same blend of hydrogen, helium, and trace metals, the same temperature, the same size, even the same flickering pattern of sunspots. This isn't just a coincidence, it's like finding your exact twin in a crowd of billions. And the implications ripple far beyond mere curiosity. The mystery begins with the odds. In a universe where stars form from chaotic clouds of gas, no two should be chemically identical. Variations in natal environments, supernova debris, and galactic recycling ensure each star carries unique signatures. Yet Sol's Echo's twin, dubbed Helio's mirror, defies this logic. Its composition aligns with our Sun's to within 0.01%, a statistical impossibility unless something extraordinary happened. One theory suggests it wasn't born here at all. Simulations show it could have been stolen from another system, a rogue star captured by the Tredecuple cluster's gravity after drifting too close. If true, its original home might have been a sibling to our solar nebula, a shred of evidence that stars can carry their birthplace's DNA across light years. But there's another, more unsettling possibility. What if this similarity isn't accidental? Certain cosmological models propose that the universe generates structures in recurring patterns like cosmic fractals. On vast scales, we see galaxies clustering in similar formations. Could stars replicate this behavior? If so, Helio's mirror might be evidence of a deeper order, a universe that repeats its recipes like a chef perfecting a signature dish. The idea tantalizes physicists, hinting that stellar formation isn't as random as we thought. Then there's the planetary question. If a star mirrors our Sun so precisely, could it host an Earth twin? Early scans reveal no gas giants in close orbits, leaving room for rocky worlds in the habitable zone. No confirmed planets yet, but the mere possibility ignites imaginations. After all, if chemistry repeats, why not biology? The system's violent dynamics make survival unlikely, but nature has a habit of thriving in unexpected places. Sol's Echo doesn't just challenge our assumptions, it holds up a mirror to them. Whether through capture, cosmic repetition, or sheer fluke, this stellar doppelganger forces us to confront how much we still don't understand about the universe's blueprints. And somewhere in its golden light, there might be answers to questions we've only just begun to ask. In the swirling chaos of Tredecuple system pulsar's quiver, gravity doesn't just pull, it sings. Here, the combined mass of 13 stars churns spacetime like a spoon through cosmic honey, creating ripples so pronounced they might soon flicker across detectors here on Earth. Unlike the violent mergers LIGO typically catches, black holes colliding in deafening silence, this system hums with something subtler. A continuous gravitational murmur, the background static of stars endlessly jostling for position. The phenomenon hinges on scale and proximity. Most multi-star systems orbit wide enough to avoid extreme spacetime warping, but Pulsar's quiver packs its stellar members shockingly close. Two neutron stars, each no larger than a city yet weighing twice the Sun, skim within 500,000 miles of one another, near enough that their gravity wells overlap, distorting the fabric of reality between them. Every time they swing past, they don't just tug at each other, they send tremors through spacetime itself, vibrations that propagate outward like ripples from a pebble dropped in a pond. What makes these ripples detectable isn't their strength, it's their rhythm. While black hole mergers produce single, catastrophic chirps, Pulsar's quiver emits a staccato pulse of waves each time its stars align. Advanced LIGO simulations suggest these micro-merger events could imprint unique waveforms onto detectors. Not the clean sine waves of colliding singularities, but jagged, asymmetrical spikes. The gravitational equivalent of a jazz drummer improvising offbeat. The real breakthrough came when astronomers cross-referenced optical data with gravitational models. By tracking the star's precise orbits, they predicted exactly when the next ripples should reach Earth, and in 2021, LIGO instruments twitched in perfect sync with the forecast. The signal was faint, buried under cosmic noise, but unmistakable. the first indirect detection of a continuous gravitational source beyond black holes or neutron star collisions. Now the hunt intensifies. If future observatories like the Einstein telescope or space-based LISA can isolate these waveforms, they'll open a new window into stellar dynamics. Each ripple encodes information about the star's masses, spins, and even their internal structures data impossible to gather through light alone. Imagine diagnosing a star's core not by its glow, but by how it vibrates the universe around it. Yet the grandest implication remains theoretical. If space-time ripples this subtle can traverse galaxies largely unchanged, they might carry whispers from the universe's most crowded stellar neighborhoods, places too chaotic to decipher through telescopes. Pulsar's quiver isn't just bending space-time, it's proving gravity itself can be a messenger, and we're only beginning to learn its language. Buried in the turbulent embrace of a Tredecuple system named Helix 23, a star shines with an eerie familiarity, its chemical fingerprint nearly identical to Earth. Known to astronomers as Terra's Echo, this celestial body doesn't just resemble our Sun in size and temperature. Its isotopic ratios, the unique blend of oxygen, carbon, and nitrogen atoms, match Earth's to an unsettling degree. It's as if someone took a scoop of our planet's crust, vaporized it, and sprinkled it into this distant star's atmosphere. The discovery sent shockwaves through the astrobiology community because these ratios aren't just random. They're the building blocks of life as we know it. What makes this match so extraordinary is the sheer improbability. Isotopic ratios vary wildly across the galaxy, shaped by local supernova, cosmic ray bombardment, and the chaotic mixing of interstellar clouds. For two stars separated by thousands of light years to share such precise ratios suggests something extraordinary, a cosmic kinship. One compelling theory traces both stars to the same stellar nursery, a giant molecular cloud that birthed them billions of years ago before gravitational tides pulled them apart. If true, Terra's Echo and our Sun might be long-lost siblings, their shared isotopic signature a relic of their shared cradle. But there's a twist that ignites wilder speculation. Among the matching elements are rare isotopes like iron-60 and aluminum-26 radioactive markers typically spread by supernova. Their presence in both stars hints they were enriched by the same cataclysmic explosion, a nearby supernova that seeded their birth cloud with the raw materials for rocky planets. That raises a tantalizing question. If Terra's Echo formed from the same stellar ashes as our solar system, could it also have spawned Earth-like worlds? And if those worlds exist, might they carry the same organic blueprints that sparked life here? This is where the line between science and speculation blurs. Panspermia, the idea that life's ingredients can hitchhike across space on comets or dust, suddenly feels less like fringe theory and more like a viable pathway. If two stars share the same isotopic recipe, could meteorites from one system have ferried amino acids or even hardy microbes to the other? The math is daunting. Interstellar distances are unforgiving, but not impossible. Recent simulations show that hypervelocity impacts, like those that might occur in a chaotic Tredecuple system, could eject debris fast enough to escape stellar gravity, potentially sending life-bearing rocks on million-year journeys between stars. The implications rewrite how we imagine life's origins. Instead of Earth being a lone experiment, we might be part of a sprawling network of chemically similar worlds, all seeded from the same cosmic reservoir. Or perhaps Terra's Echo is a fluke, a one-in-a-trillion coincidence that tricks us into seeing connections where none exist. Either way, this star forces us to confront a humbling possibility. The ingredients for life might not be rare at all. They might just be waiting, scattered across the galaxy, for the right conditions to stir them awake. And somewhere in the swirling madness of Helix 23, a mirror to our own beginnings flickers in the dark. In the gravitational whirlwind of Tredecuple systems, even planets become ghosts, appearing one moment in telescope data, vanishing the next. Astronomers tracking the system designated Mirage 9 witnessed this cosmic sleight of hand first, and when 3 exoplanets flickered into view during a routine survey, their transit signatures crisp and clear, only to dissolve like smoke when follow-up observations began. These weren't failed detections or instrument glitches. They were gravitational illusions where the combined pull of multiple stars warped space-time so severely that distant background stars briefly masqueraded as orbiting worlds. The mechanics of this interstellar deception are devilishly complex. As 13 stars whirl around one another, their gravity acts like a funhouse mirror, bending light from stars much farther away. When conditions align just right, this distortion can mimic the telltale dip in brightness of a planet crossing its host star's face. The effect is so precise that early data from Mirage 9 showed planets with seemingly stable orbits and even atmospheric signatures until astronomers realized the host star itself was a mirage, a distorted projection of a red giant 30 light-years beyond the system. But the plot thickens. Amid these false positives, one signal refuses to be explained away. Dubbed Phantom 1, this candidate exhibits bizarre behavior. Its transit depths vary unpredictably, and its orbital period shifts by hours between observations. Some researchers argue it's a real planet caught in the system's gravitational crossfire, its orbit violently perturbed by stellar flybys. Others propose something more exotic, a free-floating planet temporarily lensed by the stars, appearing to orbit when it's actually drifting through interstellar space. The most tantalizing theory, Phantom 1 might be a planet in the process of being ejected, its doomed dance with the stars stretching and compressing its transit signal like a cosmic accordion. The debate exposes a fundamental challenge in studying crowded star systems. With so many gravitational lenses at play, distinguishing reality from illusion requires watching for subtle clues like chromatic distortion, where mirage planets show wavelength-dependent transit shapes, or astrometric wobbles that betray the presence of hidden lensing stars. Future telescopes with high-precision optics might finally settle the question, but for now, these phantom exoplanets remain astronomy's ultimate uncanny valley, too precise to ignore, too elusive to confirm. What makes the phenomenon truly unsettling is its implications for the search for life. If even basic planetary detections can be faked by stellar chaos, how many other habitable worlds in multi-star systems might be gravitational ghosts? Mirage 9 forces us to confront an uncomfortable truth. In the universe's most crowded neighborhoods, seeing isn't always believing. And somewhere in that stellar storm, amid the false signals and fading echoes, there might still be real planets hiding, if we can ever tell them apart from the shadows. In the heart of Tredecuple system Stormbreak 13, the night sky doesn't just glitter. It electrifies. Here, colossal arcs of plasma stretch between stars like celestial Tesla coils, discharging bolts of energy so powerful they outshine entire solar flares. This isn't ordinary stellar activity. It's a cosmic lightning storm where ionized gas clouds act as conductors for voltages that would make earthly thunderstorms seem like static sparks. The phenomenon begins with chaos. 13 stars, each blasting out fierce stellar winds, churn the space between them into a superheated soup of charged particles. Normally, this plasma would dissipate into the void, but in Stormbreak 13, gravity holds it captive, compressing it into dense, swirling currents. When these opposing streams of positively and negatively charged particles collide, the result is catastrophic, a discharge of energy so intense it momentarily outshines the stars themselves. Telescopes have captured bolts stretching over 10 million kilometers, longer than the diameter of our sun, crackling for hours before fading into the dark. What makes this lightning so alien is its fuel. On Earth, lightning requires water droplets and ice crystals to separate charges. In Stormbreak 13, the mechanism is far more exotic. Ultraviolet radiation from the stars strips electrons from atoms, creating a seething mass of ions and free electrons. Magnetic fields twisted by the star's rapid orbits then whip these particles into frenzied motion, separating charges like a cosmic Van de Graaff generator. When the imbalance becomes too great, snap, a bolt lances across the void, sometimes striking nearby stars, their magnetic fields redirecting the energy into dazzling auroral rings. The storms follow rhythms as unpredictable as they are beautiful. Some days the system crackles with hundreds of micro-discharges, flickering like a broken neon sign. Other times it builds toward a single apocalyptic strike, a hyperbolt that releases as much energy as a small supernova in mere seconds. One such event, observed in 2022, left a nearby gas giant scorched, its atmosphere ionized down to the mantle. Yet the greatest mystery isn't the lightning, it's what triggers the largest surges. Researchers suspect hidden players, rogue planets or neutron stars skirting the system, their gravity stirring the plasma like spoons in a battery acid bath. Others propose the stars themselves are the architects, their overlapping magnetic fields creating temporary circuits in the plasma, focused enough to channel energy across light years. Stormbreak 13 doesn't just defy expectations, it rewrites the rules of plasma physics. If charged particles can organize on this scale, what other cosmic phenomena might we be missing? And somewhere in that electrified chaos, the universe is proving that even the void between stars is anything but empty. It's alive with currents we've only begun to measure, and every bolt is a reminder, out there the rules are still being written. Flitting between the gravitational chaos of a Tredecuple system, frozen relics from the dawn of time refuse to melt into oblivion. These aren't ordinary comets, they're cosmic time capsules, their icy cores packed with dust grains older than our sun, surviving against all odds in a furnace of 13 stellar infernos. Designated the Chrono Comet Cluster, these primordial snowballs should have vaporized eons ago under such intense radiation. Yet here they thrive, their chemistry rewritten by the very stars that sought to destroy them, offering a glimpse into the universe's raw ingredients unlike anything in our solar system. The survival of these icy nomads hinges on a delicate dance between destruction and renewal. In single-star systems like ours, comets bake steadily as they approach the sun, shedding surface layers in predictable jets. But in this Tredecuple maelstrom, the rules shatter. When a comet drifts too close to one star, ultraviolet radiation blasts its surface, cracking apart water molecules and forging hydrogen peroxide, a reactive compound that acts like antifreeze, preventing deeper ice from vaporizing. Before the damage becomes fatal, the comet gets slingshot toward another star, where stellar winds blast away the damaged crust, exposing fresh primordial ice beneath. This cycle of scorching and scouring creates a bizarre form of preservation, like a fruit being repeatedly peeled yet always revealing unblemished flesh underneath. What makes these comets truly extraordinary is their cargo. Spectroscopy reveals molecules thought to vanish billions of years ago, prebiotic compounds like formaldehyde and methyl cyanide, the building blocks of amino acids locked in ice that's never fully melted. Some even contain microscopic diamonds, forged in the shockwaves of ancient supernova before our solar system existed. These aren't just relics, they're frozen recipes from the universe's first kitchen, ingredients that might have seeded life elsewhere. The real surprise came when astronomers detected isotopic anomalies in the comet's oxygen, ratios patterns that shouldn't exist if they'd formed locally. The most likely explanation, these icy bodies are interstellar fugitives, captured by the system's gravity after drifting for eons between stars. Their chemistry matches clouds in the Orion Nebula, suggesting they're visitors from a stellar nursery light years away, preserved by the Tredecuple system's unique radiation ballet. Now, the ultimate question, could these comets have delivered life's precursors to planets within the system? With 13 stars stirring the pot, any organic payload faces brutal odds, but nature loves proving us wrong. Recent models show that certain orbits could shepherd comets into stable zones between stars, where icy crusts might shield delicate molecules for millennia. It's a long shot, but in a universe where frozen time travelers outwit stellar furnaces, anything seems possible. And somewhere in those glittering ice fields, the universe's oldest secrets wait, whispering stories of a time before stars had companions. Among the whirling chaos of Tredecuple system paradox cradle, the stars tell two wildly different stories, one of ancient fading embers, the other of blazing stellar newborns. Here, 3 ruby-red giants older than our Milky Way orbit alongside 10 blue-white stars, so young they haven't finished burning off their birth clouds. This cosmic family portrait shouldn't exist. Stars born together age in lockstep, like classmates growing grey at the same rate. Yet somehow, Paradox Cradle's members span a 12-billion-year age gap, a discrepancy so baffling it forced astronomers to rewrite the rules of stellar kinship. The mystery deepens when you examine the evidence. The ancient red giants show telltale signatures of metal-poor population Roman II stars, relics from the universe's first 2 billion years when heavy elements were scarce. Their younger siblings, by contrast, glitter with metals forged in countless supernovae, their spectra screaming modernity. They shouldn't share an orbit any more than a caveman should share an apartment with a smartphone developer. So how did this cosmic odd couple form? One electrifying theory suggests a stellar kidnapping. Around 600 million years ago, Paradox Cradle's original stars, all ancient, drifted too close to a roving star cluster fresh from a galactic collision. The violent encounter could have ripped away most of the system's original members while depositing a new generation of young stars captured from the cluster, like cosmic pirates swapping hostages during a skirmish. Supporting this, the system's motion traces backward along the Orion Cygnus spiral arm, a region littered with the debris of past galactic mergers, but there's a rival explanation that's even stranger. Some models propose the young stars weren't adopted, they were resurrected. When galaxies collide, shockwaves compress dormant gas clouds, triggering furious new rounds of star formation. If Paradox Cradle once orbited such a collision zone, turbulence might have reignited nuclear fusion in half-dead stellar cores, essentially hitting the reset button on their aging process. The rejuvenated stars would carry chemical memories of their true age while burning with youthful vigor, creating the illusion of mixed generations. The most tantalizing clue lies in the system's lone pulsar, a rapidly spinning neutron star that acts as a cosmic clock. Its deceleration rate suggests it's nearly as old as the red giants, yet it's magnetically entangled with 3 of the youngest stars, an impossible relationship unless some cataclysm forcibly bonded them. Whether through adoption, rebirth, or some undiscovered stellar alchemy, Paradox Cradle stands as a living fossil of the universe's turbulent past, and somewhere in that mismatched family, the secret to cheating stellar time might be waiting. Deep within the tangled orbits of Tredecuple system Kepler's maze, one star flickers like a faulty light bulb, its erratic dimming patterns so bizarre they sparked an interstellar detective story lasting more than a decade. Catalogued as KIC star 9, this stellar oddball experiences deep, irregular brightness dips, sometimes losing up to 20% of its luminosity for weeks before snapping back to normal. The patterns refuse to follow predictable cycles, ruling out planets or typical dust clouds. When astronomers first published the data, one radical theory exploded across scientific circles. Were these the telltale shadows of an alien megastructure, a Dyson swarm under construction? The Dyson hypothesis hinges on scale and precision. In theory, an advanced civilization could harvest stellar energy by building orbiting solar collectors, whether solid shells or swarms of smaller panels, that would periodically block starlight as they passed our line of sight. KIC star 9's dips seemed eerily structured for natural phenomena, with some light curves showing geometric shadows unlike the soft curves of transiting planets. Researchers even identified one sequence where 79 separate dimming events followed a Fibonacci-like spacing, a pattern that sent technosignature hunters into overdrive. But the cosmos rarely yields to easy answers. Competing natural explanations emerged. One camp pointed to colossal starspots, magnetic blemishes hundreds of times larger than our suns, that could darken portions of the star as they rotated into view. Another faction argued for circumstellar debris. Think Saturn's rings, but scaled up to nightmare proportions, with trillions of dusty fragments from a recent planetary collision casting jagged shadows. Supporting this, infrared telescopes later detected excess heat around KIC star 9, consistent with warm dust rather than cold megastructures. The plot thickened when spectrographs revealed the star's chemical fingerprint. Unlike normal stars, KIC star 9's atmosphere shows bizarre depletions in elements like silicon and magnesium, materials that should be abundant unless something has been actively filtering them out. Could this be evidence of star mining and alien civilization extracting raw materials for construction? Possibly, but nature offers an alternative: vaporized planets. If a gas giant spiraled too close and was torn apart, its silicon-rich core could have temporarily polluted the star's outer layers before heavier elements sank out of sight. Now the theory gaining traction involves none of the above. Recent radio observations caught KIC star 9's siblings in the act 5 near by stars emitting synchronized flares whenever the dimming events occur. The best explanation: a vast, magnetically charged dust cloud trapped in orbital resonance with the stars, warping and reforming under their gravitational tides. As plasma arcs between the stars, they superheat pockets of debris into temporary opaque screens, creating shadows that wax and wane with stellar activity. Yet the allure of cosmic archaeology lingers. Even if natural, this system showcases phenomena so extreme they stretch our definitions of possible. Whether through alien engineering or nature's own grand designs, KIC star 9 proves the universe needs no help building mysteries. It architects them effortlessly, leaving us to decipher the blueprints. And somewhere in those flickering shadows, whether from dust or Dyson spheres, the line between science fiction and astrophysics grows deliciously thin. At the heart of a Tredecuple system dubbed Tempest's Legacy, 2 stars defy the cosmic rulebook, locked in a tight binary embrace while hurtling through the galaxy at nearly 2 million miles per hour. This hypervelocity duo, catalogued as Binary X, moves fast enough to cross the Milky Way in just 50 million years, leaving their 11 bewildered siblings behind like spectators at a cosmic racetrack. The question isn't just how 2 stars became so impossibly fast, but what role the system's chaotic family played in launching them toward interstellar exile. The answer lies in gravitational billiards on an epic scale. In most star clusters, close encounters might nudge a star into a slightly faster orbit, but Tempest's Legacy is no ordinary playground. With 13 massive stars crammed into a region smaller than our solar system, the math becomes explosive. Simulations suggest that about 800,000 years ago, Binary X drifted too close to a tight trio of stellar siblings, 3 blue giants whose combined gravity acted like a cosmic slingshot. As the binary pair swung past, they stole a fraction of the trio's orbital energy, accelerating with such violence that they shattered the system's gravitational shackles entirely. But speed alone doesn't explain the binary's survival. Hypervelocity stars usually tear apart during ejection, their mutual gravity too weak to withstand the acceleration. Binary X's secret, a quirk of timing. Just before their fatal encounter, the 2 stars had dipped into an unusually close orbit, close enough that their mutual gravitational bond became unbreakable, like climbers roped together on a mountainside. When the slingshot hit, that bond transformed into a lifeline, allowing them to anchor each other against forces that should have ripped them apart. The fallout from their escape reshaped the entire system. The energy stolen during Binary X's launch sent the three blue giants recoiling inward, triggering a chain reaction of destabilized orbits. One star spiraled into the system's core, colliding with a neutron star in a cataclysm that lit up the galactic sky for weeks. Two others were flung into opposing elliptical orbits, their paths now weaving dangerously close to remaining siblings. Meanwhile, the 11 stars left behind seemed to bear gravitational scars, subtle wobbles in their motions hinting at the violence of that ancient parting. Yet the most astonishing twist isn't their speed, it's their future. Most hypervelocity stars are condemned to drift alone through the galactic void, but Binary X carries a flicker of hope. Spectrographic analysis reveals they're trailing a tenuous stream of gas, a wake of material stripped by their passage, like breadcrumbs marking their path. Some theorists speculate that in another million years, this trail might collapse under its own gravity, spawning new stars along Binary X's flight path. A hypervelocity legacy rewriting the galaxy one light year at a time. Tempest's legacy doesn't just challenge our models of stellar dynamics, it reveals a universe where chaos and kinship collide. In the grand pinball machine of the cosmos, sometimes the most violent kicks don't just send stars flying, they bind them tighter together, proving that even in the vastness of space, no act of destruction is ever truly solitary. And somewhere in that binary's wake, the other 11 stars still spin, their gravity humming a silent requiem for the siblings they lost to the void. In the celestial chaos of Tredecuple systems, where gravitational anarchy usually reigns, one rare gem defies the odds: Harmony Prime, a cosmic timepiece so precise its eclipses tick like a metronome set by the universe itself. Every 13 years, without fail, 3 of its stars align in flawless syzygy, casting shadows so crisp and predictable they might as well be etched into the fabric of spacetime. This isn't just luck, it's orbital poetry, a ballet choreographed by the delicate balance of mass, momentum, and sheer cosmic serendipity. What makes Harmony Prime's clockwork so extraordinary is the fragility of its perfection. Most multi-star systems are gravitational minefields, where even slight nudges send orbits spiraling into disarray. Yet here, 3 stars dubbed the Trinity have settled into resonant orbits, their periods locked in a precise 3:2:1 ratio. Imagine 3 pendulums swinging in sync. The innermost star completes 6 orbits in the time the middle star finishes 4, while the outermost star lags at 2. This harmonic rhythm ensures their eclipses repeat like pages in a celestial calendar, their shadows crossing at intervals so regular you could set your watch to them if your watch spanned light years. The secret lies in their birth. Unlike most Tredecuple systems where stars form in turbulent bursts, Harmony Prime's Trinity likely condensed from a single, unusually smooth gas cloud, their orbits preserved like flies in amber. Computational models suggest their cradle lacked the violent interactions that typically scramble stellar paths, leaving their delicate dance undisturbed for billions of years. Even the system's 10 other stars, though chaotic, orbit at a respectful distance, their gravity too weak to disrupt the Trinity's precision. Yet the real marvel isn't just the predictability, it's the light show. When the Trinity aligns, their combined gravitational pull warps spacetime enough to lens background starlight into glowing rings around the eclipsing pair, a phenomenon called an Einstein halo eclipse. For days, the system's glow pulses with iridescent ripples, as if the universe itself were applauding the performance. Harmony Prime doesn't just defy chaos, it redefines it. In a cosmos where randomness rules, this system stands as proof that even amid turmoil, pockets of order can endure. And somewhere in those fleeting eclipses, there's a whisper: perhaps the universe isn't just a storm. Sometimes it's a symphony. From phantom stars and diamond cores to vampire suns and stolen light from the future Tredecuple star systems aren't just cosmic oddities, they're the universe's ultimate physics playgrounds. These 13 star chaos factories have rewritten the textbooks, proving that gravity isn't just a force, it's a mad scientist, conducting experiments too wild for our labs to replicate. Think about it. We've seen stars vanish into gravitational mirages, watched planets form inside warped spirals of dust, and even caught a stellar chorus singing in perfect Fibonacci harmonies. These aren't just discoveries, they're cosmic daredevils, challenging everything we thought we knew about how stars live, die, and occasionally cheat the rules. Take Orion Complex 13, where 13 stars move like a swarm of angry bees, defying every orbital prediction. Or Kappa 13's phantom eclipses, where stars blink out like cosmic streetlights on a timer no one set. Then there's the radio screamers, blasting pulses so precise they had scientists whispering about alien megastructures, and Anchor 13, where dark matter itself seems to be playing puppeteer, holding the system together with invisible strings. And who could forget Crimson Cluster's vampiric devourer, a star so gluttonous it's been feasting on its siblings for millennia, or Symphony 13, where orbits move to a mathematical rhythm older than human music. But here's the real kicker. These systems aren't just freak shows, they're clues. Every time we crack one of their secrets, like how Mirage 13's invisible star bends light without emitting any, or why Harmony Prime's eclipses tick with atomic clock precision, we're not just solving a puzzle. We're peeking behind the curtain of reality itself, learning how gravity stitches the cosmos together in ways we're only beginning to grasp. So tell us, which of these 30 discoveries left your jaw on the floor? Was it the runaway star fleeing at 1/10 of light speed, the diamond core glittering in a stellar furnace, or the quantum-entangled twins moving in perfect sync across light years? Drop your pick in the comments. We read everyone, and if you're hungry for more cosmic chaos, hit that subscribe button. The universe has plenty more surprises up its sleeve, and we're just getting started. Until next time, keep looking up, because out there in the dark, the stars are still writing the rules.